Hello again, everybody, and welcome to Lab Talk number 30. It's Elektor's chat about the latest in electronics, embedded systems, and AI. And I'm Brian Tristam Williams, and today we're exploring the highlights of our March-April issue, and we're talking about RISC-V, FPGA development, AI at the edge, and some exciting hands-on projects. So, joining me now, as always, is our editor-in-chief, Jens Nickel.
Hello, Brian.
Hey, Jens, how are you doing?
I'm
great,
very
thanks.
fine. I'm actually sitting in Cologne where the carnival season begins, but I'm not right in the inner city because I think I couldn't do a silent live stream. So
might be a bit difficult with the party going on, although I believe we're all having rain outside, you and I.
Yes.
And also with us is our special guest, Dr. Christian Nöding, who contributed an in-depth project on FPGA-based digital audio mixing using an Arduino MKR Vidor 4000. Chris, how's it going?
Hi, thank you. Thank you to be here. It's a great honor.
Thanks.
I'm fine.
And can't wait to talk to you. You've got a lot of interesting stuff to show us. But before we go there, let me tell you about our sponsor, EE News Europe. If you're looking for the latest electronics and engineering news, check out eenewseurope.com, which is an Elektor International media publication. EE News Europe is a fully digital publication covering the global electronics market with specializations in analog, automotive, embedded power, smart 2.0, wireless technologies. So read eenewseurope.com and subscribe to its newsletters to stay informed about essential industry news, key events, and technological innovations. Of course, our regular audience will want to know about our upcoming giveaway. We're giving away an iCEBreaker FPGA board. It's a fantastic open source FPGA development platform, perfect for learning and experimentation. It supports open source tools like YOSYS, NextPNR, iStorm, and Amaranth HDL, making it great for workshops, personal projects, or just getting started with FPGA design. So to enter, we'll give you the link and the code word later. So stay tuned to about the bottom of the hour, and we will share the code word with you. Good luck to the audience, and hello to you all joining us from around the world. Now, back to Jens and Christian. Jens, how did you find the article on RISC-V for the new edition?
That is, in fact, our cover article for the next edition, which has traditionally the topic embedded and AI, because, that's a little bit also because there's the embedded world going on. So March, April, we are traditionally reporting on AI and embedded. And I think it was the last embedded world where RISC-V booth was really near our booth. And there were a lot of boards presented. So the whole team, whole editors team, also our CEO and so on, we really had fun in watching all this. And we said we should definitely report on RISC-V. And as you know from Elektor, we will do it in a more practical approach. Of course, we have in this cover article also some basics about RISC-V, but the main part are presentations of boards, and not only very powerful boards featuring very powerful processors and peripherals, what the heck, HDMI and camera interfaces and so on. We also have very small boards, and there, from my eyes, there it gets very interesting, because we also have a board, I think for some euros, which has a controller on it for exactly 10 cents.
Wow.
So that is really a number for a 32-bit controller. And I can already announce in the next edition there will be an in-practice article about how you can work with this 10-cent controller. So it's definitely worth to read, but that's not the only article we have in that edition. We will come later to that FPGA article, and there we invited the author and the creator of this project. which is quite interesting. And then we have other nice projects, for example, from our colleague Saad. He's featuring a sensor test board that is really nice design. You have some motherboard, and you can put in other small boards with different sensors on it, so you can evaluate very fast different sensors. And we have many other articles. We have, for example, an article about parallel programming of a Raspberry Pi Pico. We have a very nice article. Yeah, Brian is showing at the moment an environmental monitoring system, and we have another nice article about a project which is called MCU Vidor. And for all controllers, for all boards which has a JTAG or ST-Link interface, you can use your probe with that tool, which is a very nice graphical tool to have a look on all the variables, and also have a trace view of very fast signals. And yeah, the interesting thing is that that tool was also created by a hobbyist, so to say, in a semi-professional way or even professional way. But yeah, for me, it's a very nice example that also hobbyist projects can really grow and can really come to a very high quality. And the same goes for the FPGA player that Chris is later reporting on.
Yeah,
so
since I'm driving the magazine, just tell me if you want me to go to a specific page that we can jump to Chris's article.
Yeah, I already gave you an overview, so it's an edition definitely worth to read. There are also news from our colleagues from EE News in there, and yeah, we selected quite nice ones reporting on different really sophisticated things. I'm impressed what's going on at the moment, from AI processors to quantum processors and different things. And yeah, the colleagues from EE News, they are really at the head of these developments, which are sometimes in research phase. But who knows, maybe in 5 years we will have our first AI, really AI computers on our desks. Yeah, it's starting right now. And yeah, I read that they currently are developing a quantum computer which is really portable, so to say. And yeah, there are many things going on, and our colleagues from EE News, they report regularly on all these new things.
Yeah, I think they contributed 16 bonus pages. Very interesting stuff.
Yep.
And of course, I had some fun with the project, part one of this MIDI synthesizer. As I explain in the article, I bought this keyboard behind me because my old keyboard broke, or I broke it by mistake. But this one could put out sound, and my new one doesn't do any sound. It's MIDI only. And I thought, that's not a problem. I'll just plug it into my PC. No, it turns out that's actually a hassle when you just want to play. So I started off using a Raspberry Pi as a MIDI synthesizer. I mean, there's a synth right there, as you see, but it's big and it's heavy and it's old and it uses a lot of electricity. But solved the problem. Raspberry Pi to the rescue. And it's even powered by the keyboard's USB. So it's really simple, and naturally you want to run it headless. You don't need a keyboard and monitor. Just power up and it's your synthesizer dedicated to the task. That was fun. Back to table of
definitely
contents.
Also a project you should work on, Brian. I already read the second part. And yeah, interesting approach.
Yeah, the first part was just getting the Raspberry Pi to be a synthesizer, and that worked, so I was encouraged by that. Now I want it to be my AI playmate, so when I'm playing music, it can join me and do some things in the background. So we'll see in part 2 coming up in May. Okay, shall we jump to this very interesting article on an FPGA-based audio player, also part 1, with equalizer. And Chris, what made you decide to use the Arduino MKR Vidor 4000? That's a mouthful.
Yeah.
I've never seen it used before.
Good question. When I thought back to my study, I never learned VHDL, and I was curious about how FPGAs are working. And for me, I need some projects where I can see something, hear something, or feel something. Sometimes feeling is not the good way in electrical engineering, but hearing and seeing is a good thing. And yeah, I was curious about how these things can handle digital audio streams. And I searched around and found this MKR Vidor 4000 board and searched around what other people did with this project or with this board. But then I saw that, yeah, this board is not well used in the internet. Some special things, some examples how to use HDMI and so on. But yeah, this gave me an idea to test what can we do with this board. First, I tried to use this board to make a double pulse generator for my work to measure semiconductors. But then I realized with this FPGA is much more possible than outputting simple pulses. And I started to decode or try to decode digital signals because some months ago, I bought a defect product from Behringer. It was not working anymore, and someone connected the plugs in the wrong way and destroyed the output stage. But the digital system was still working. And yeah, and I tried to figure out what I can do with this Vidor 4000 and if I could connect it to this Behringer device. And in the end, this audio player was the result. So part for part, I added more functions. It started first with some very simple volume control. And afterwards, I thought about what can I do to get the volume, the sound under control, so the equalizing. And then I studied some papers how to create some effects like IIR filters and tried to implement this. And yeah, several GitHub projects were very helpful at the end. But yeah, at the end, I created a whole digital audio mixing system with a latency of about 20 microseconds. So this means real time. This is really great. And everything with this simple board. And this was great.
Well, that's awesome. 20 microseconds. That's now
only one sample.
And just tell me when we need to put up your screen, because you've got some stuff to show us as well.
Yes.
Are you saying that you never did FPGA before?
That's right. This was my first project, and I started learning VHDL with this. Let's try to present my slides. Give me a second. Yeah, it seems to work now. So could you share it on the stage, or maybe you already did this?
Already did, yeah. That's
okay.
That's your live camera.
I hope now it is working, right?
I'm seeing your biography. Your bio.
Yeah, great. Okay. Yeah, okay. Maybe we can start with this. So I prepared 3 topics for today, and maybe step by step we talk about the first topic here, this FPGA-based audio player. And just to give you an idea of what I did in the past. So this is the device in the upper left corner, which I bought on the flea market. It's this Behringer P16i. It's a device where you can put 16 analog signals into it, and the lattice FPGA on this board converts everything to a 2-signal digital audio stream with each 8 channels. And as I said, the output stage was not working anymore. You can see here in the green rectangular, there are some output buffers, and everything above these buffers is not working anymore. Yeah, my first idea was to... Yeah.
Chris, if you say analog signals, where is the conversion to digital? Is it inside the FPGA, or are there dedicated ADCs?
Yeah, they are dedicated ACs. Here, as you can see here in the red in rectangulars, it's 8 2-channel audio ICs. It's from Asahi Keizai. I don't know if I spell it right.
And then
It's
it's I2S to the FPGA, or what is the?
This is a good question. I did not have a look at this. This is maybe another project, but I think so, yes.
How do you do it? How do you get audio signals in your FPGA?
Yeah, I will show you this in the live demo a couple of minutes later, but I used I2S2, but another protocol, this Behringer P16i, was supposed to output Ultranet. And this Ultranet transmits 8 audio channels per line, and there are 2 lines in total, so 16 24-bit audio lines. And this is a multiplex signal where the clock is inside the data signal itself. So many of you are maybe familiar with this AES3 or AES-EBU is the system called. The same signal home AVRs are using for outputting 5.1 audio for the home cinema, more or less. It's not really the same, but comparable. Yeah, and as an electrical engineer, I was curious about what is not working with it. I saw that the output buffer are not working anymore. But then with my oscilloscope, I saw that the input stage of the buffers are still working and that there's a multiplex signal. And then I used my FPGA to have a look at the signals itself and try to decode it. And yeah, the possible audio sources at the end with this project we are showing in the next Elektor issue. We can play SD card audio, so this means MP3 and WAV. For this, the Arduino libraries are really, really great. I did nothing here. I just imported the libraries and reading audio files to one of the chips on this maker board. Here you can see in the left corner, it's the green highlighted chip. It's an ESP32. And the module is called Nina W102, but it's in fact an ESP32, and you can use it with the Arduino IDE. And yeah, in the red highlighted chip, this is the FPGA. It's from Intel, now Altera, a Cyclone 10LP, so a low-cost FPGA with only 16,000 logic elements. I think the largest FPGAs have something around 400,000 logic elements and even more, but then they are quite expensive.
So maybe to give the readers a quick picture who haven't read your articles. So you are inputting some signals to the FPGA, analog ones and also digital ones. There are several options. In the FPGA, you do all the masks. So you do you mix and you do volume control and filtering, and then you have several outputs.
Yeah, that's right. Exactly. It depends on you, what kind of outputs you like to have. The FPGA has a lot of free logic. If you remove some of the parts, so maybe you can have only 2 or 1 of the equalizers instead of 5, then you have spare logic elements and you can put more outputs, more output channels. And yeah, we already talked about I2S, so I'm not sure if we should go too deep into this, but this is the signal I used internally in the FPGA. So I put in I2S to the FPGA, and the Ultranet, so this AES-EBU signal, is converted internally in the FPGA to I2S2. And yeah, I decoding this, and in the Elektor article, we described everything in detail. So I think without going into the VHDL code itself, this is the only logic we have to build in to decode I2S signals. And this is really great. I think the whole sequence, the whole file was something around 100 or 120 lines of code. It was not so much with comments. And yeah, that's the input stage of the audio player, or maybe audio mixer at the end. So we have analog input, SD card input, the Ultranet with 16 channels, and then some UART control from the computer or from the web interface. We will have a look a bit later into this control mechanism. Yeah, and then we have the output mixing stage where we take all input signals. Each input signal here and in this stage is presented as a 24-bit logic vector. So 24 individual bits, that could be 1 or 0, and these are representing PCM samples. Every computer is dealing with this if you have a WAV file. So uncompressed audio and the full dynamic range of 144 decibels here. So plain audio without losing some kind of quality. And after the audio mixer, I placed some IIR filters. And again, without looking at this equation in detail, we only need some sums, some subtractions, some multiplications, and maybe a look at this graph is a bit easier. We only have to store 5 values at the end. 2 values for the input and 3 values for the output. And with this, we only have a memory, internal memory of 96 bits. And with this, we can create an IIR filter, which can be a peak filter, a high pass or low pass, and everything else. This is the whole math.
I see.
And yeah, here you can see the whole processing within this audio mixing console.
What
it is
what
something
is the
like this.
sampling rate you are working with?
That's the great thing of FPGAs. It does not depend, or it depends on the input. So in general, it is 48 kilohertz, but the FPGA is clocking with about 100 megahertz, and you can increase the sample rate of the audio as you like. So 96 or 192 kilohertz is no problem here. The only thing was the ESP32 had some limitations, and there it was limited to 48 kilohertz. But my analog input stage here sampled at 192 kilohertz, and the whole FPGA could do this as well. So great thing.
Have you made tests? Because I'm also working on an audio project, and my limitation is at the moment 32 kilohertz because of the limited data rate. But I made also tests with 32 kilohertz compared to 48 kilohertz, and I rarely hear a difference. I think a CD quality is a little bit in between. It's 44.1, but it's very hard to hear differences between 32 and 48. I think that has maybe something also to do with the age of the one who is listening, because if you are older, you don't hear the very high frequencies.
Yeah, that's right. The Christmas is losing.
Yeah, I see a big difference when it comes to 24. So that is definitely, I think, too low. But
yeah. Thinking about Shannon, you have only half of the frequency there. Yeah,
I think 48, you are on the safe side, and I think even higher sample rates, they are maybe good for doing math, exactly as if you have an even higher resolution, you can do some math with it. You are
I think my high frequencies have dropped off a lot since I was younger. I used to be able to hear the 15,625 hertz scan of the TV, but now I can't hear that anymore.
Yeah, no.
That's normal.
Yeah, that's right. As you can see here in this graph,
the chat room. Just want to get to the chat room here. John M from North Carolina says he has tried to use the Vidor 4000 a while back for object identification using an OmniVision OV5647. He found the tools a bit challenging, but perhaps they have gotten better. I don't know anything about FPGA. I mean, I've been interested in it since the 80s, when cartridges for your home computer used to usually be traditional EEPROM or some other kind of memory, and then someone released a cartridge that was fully FPGA based, and I found that very, very intriguing. But you have gone down the road of recreating. I mean, you wouldn't need a traditional DSP either, because you've pulled this off with very high quality analog audio.
Yeah, in this project, this is pure logic, so there is no DSP processor involved. And yeah, for the image recognition, that's right. I think this is one of the examples they presented with the HDMI output, and you can connect a camera to this Vidor 4000 board that is able to recognize. This is one of the things I'm planning to do for audio, to recognize audio events and maybe some kind of mixing, auto mixing function based on the audio signal. But that's yeah, something for AI and maybe 2028.
Just want to get
regarding, I think regarding the FPGA tools, I think these are the normal tools from the FPGA manufacturer. Chris?
With the tools
the
I
IDE,
used, yes.
the IDE to program the FPGA.
Yeah, I'm using Quartus 20.
Quartus.
Which version is it? 2022, I think. Yeah, one of the free versions. It's Quartus Prime Lite. You can download it from the Intel or now Altera webpage. They changed the name again. And it's absolutely free to use. And this Cyclone 10 LP with 16 kilo logic elements is fine for the Web Lite edition. So you can use it for free. Was it difficult to learn for you to dive in that tool, and how did you do it? With videos? Yeah. Yes. YouTube was quite helpful. There are several, I think 2 or 3 VHDL free VHDL YouTube channels that explains it really good. But I learned that Verilog is the more important language in the US American area. But I started with VHDL, so I never learned Verilog in detail. And I kept now for VHDL. So sometimes it is a bit hard to get learning material for VHDL. But yeah, I started, as I said before, with some kind of double pulse generator. So the very easiest task you could imagine with VHDL. And this audio processing was several months later. So I had a soft start and could learn VHDL from scratch. Yeah.
Another comment from John is that the Vidor 4000 is end of line from Arduino. Is there a path forward if you can't get that? Yeah. Bit of a tragedy, but surely there is a replacement available.
Yeah, I hope so. I'm planning to get in touch with the Arduino guys on the embedded world in 2 weeks, and this would be my next question if there is a follow-up. But I didn't know that it is end of life now, so I hope they will bring out a new FPGA board. But there are several other boards, but not with the combination of 2 microcontrollers and the FPGA.
That is the interesting thing, because Chris, you are explaining very well in the article how easy it is to integrate, so to say, FPGA configuring file in the Arduino code.
Yes, right.
Exactly. That is a nice thing. So you can first compile it, so to say, and then integrate it in the sketch, which is a nice way.
Yeah. I like what you've called there your DIY SD card adapter. You just soldered right onto the pins here. Is that right?
Yes, I was lacking of some professional adapters, so I had a lot of spare adapters here for micro SDs. And yeah, these adapters have some connectors on the back. It's quite small, but it was fine for me to solder some cables here and connected it directly to the Vidor 4000. And yeah, it is working fine, but you have to keep an eye on your frequency, because SD cards are using SPI protocol. And first I tried it with the full frequency. So I think it was around 24 or maybe 30 megahertz. And with some loose cables, this was a problem. So I went down to 60 megahertz and then it was working fine. Maybe you should start at 8 or 12 and then go up if something is working, and it's a good starting point here. But it's a very easy and cheap adapter.
Yeah, easy and cheap, and would have made me nervous to be soldering so close to the plastic bits, but you've given me courage to
I had several tries because I had a staple of them, so I think 20 or 30 of these adapters, so it was fine.
Nice. Well, John does say hats off to you for being able to pull off this project.
Okay, thank you.
And I see we're at the bottom of the hour, so let me keep my word to the audience, and I'll swap screens with you briefly. There is our giveaway page. This is the URL and the code word. I kept it nice and simple, just MKR Maker. So good luck join the competition, and one of you will win an iCEBreaker FPGA Development Board. Back to Chris's screen.
Yeah, okay. I think my next slide is live demo, and I think we are talking about audio devices now, or DIY audio systems, and I think it's time to show what this thing is capable of doing. Yeah, if you compare this graphic here with this, you can see there are more cables than before, but this is only because I tested some HMI, so user interface, with this display here and some buttons and a couple of more things. And I hope everything is working. I tried this, but I never did this live.
Chris, can you briefly explain what we see here? What are these different
Yes, sure.
ports? Mm-hmm.
Yeah. Behind this cables, there is the Vidor 4000. So it is responsible for receiving all digital signals. It's responsible for reading SD files or WAV files, MP3 files. And the many cables here are connected to, I hope I do not create a short circuit. Here's a joystick and some buttons to control my LCD. So the whole left part on your monitor is only for controlling, but the decoding is done over these few cables here. And I have here some evaluation board for an audio stereo ADC from, I don't know, it's from Texas Instruments. It's a well-known ADC, which is capable of 32 bits and 192 kilohertz. So quite high spec. And I connected this ADC via I2S. We already saw this communication to my Vidor 4000, to the FPGA. Then the whole mixing process is done. And then I connected here a standard or very cheap converter from SPDIF to an analog system. And I switch my microphone now.
So you give out the audio result as SPDIF, and your converter is converting it to analog, and this sound we will hear.
Yeah, right. I hope you can hear me now, because now you hear me through this device. Is this working?
It's a bit low, audio-wise.
Yeah. It's too. Okay, I go a bit up. Okay, I hope I go a bit closer here. Now you can hear me now here. Yeah. First, for this stream, I tried to demonstrate this Sigma Delta conversion, but I had a bit trouble with my audio interface, and even by using a DI box, I had some ground loops and some humming. So yesterday I switched to this converter box to stay safe. But anyway, this Arduino or this FPGA is capable of outputting pure analog signals over a Sigma Delta conversion, but this is maybe part of the third article, maybe, or have a look at my webpage or the GitHub project. And yeah, we can have a look at the interface. I have to find my screen of my mobile phone, because everything is controlled by a Wi-Fi interface, and it's great what is possible today with some standard libraries and some projects from the internet. I'm using Bootstrap here, or maybe I can switch back to my other mic for first. And yeah, you can see here it's quite responsive.
Your volume is too high.
Sorry, so I go down a bit. I hope this is fine again.
Yeah.
Okay. And yeah, you can see here, you can change the speaker volumes, the balance, subwoofer, because I implemented a crossover here in the FPGA to separate the highs and the lows for a subwoofer. And there's a channel mixer for SD card, for the mic level, and Bluetooth. But yeah, the Niner module has Bluetooth, but the internal storage was so low that I couldn't enable it when using the Wi-Fi. So I had to decide Wi-Fi or Bluetooth.
Yeah, what we see here on your phone, that is a web page which is offered by the ESP32. Do I understand?
Yes, right. Yeah,
okay.
Exactly.
That is, impressive user interface and you are doing that with that Bootstrap framework.
Yes, exactly. Yeah. And everything is stored on the SD card. So if you like to change something in the user interface, you can pull out the SD card, put it in the computer, change the the web page, and then you can get it back.
What is the size of the what is the file size approximately?
Only some kilobytes. First, I tried to shrink everything into the ESP. So I think the Bootstrap was the largest size, about 150 or 180 kilobytes, so nothing more. So at the moment, I think it's an 8 gigabyte or 4 gigabyte SD card, so it's plenty of space here. And yeah, just play some sounds. I switch back to the input.
It's very soft again.
Okay, I only wanted to demonstrate that SD card files could be played. And yeah, you can do everything with this technology basis here. You can create a multi-channel audio player. You can create a multi-channel audio mixer, a Bluetooth receiver, a multi-audio channel Bluetooth receiver, if you like. One of my thoughts about what I will do with this is multi-audio amplifier, so that I could get real surround sound with about 20 speakers, small speakers around me, and I just want to see if this is much better than the virtual surround sound with 5.1, but it's in the very, very early planning phase. But this could be one of the technology bases for this.
We have a question here. What are the advantages of using an FPGA for audio processing instead of a traditional microcontroller or DSP?
Yeah, we have to separate between DSP and microcontrollers. Maybe microcontrollers first. They are really great in processing large calculations, like the equalizer informations. I had to calculate very large multiplications and had to deal with square roots. I had to calculate divisions and so on. This is really bad for FPGAs, but a microcontroller can deal with it very easily. And floating point values are very easy because we have an FPU in the microcontroller. So this is everything a microcontroller should handle. But if you are dealing with live audio with very low latency, then you should use a DSP, so a digital signal processor. And a DSP is a very specific FPGA, if you like, something like this. And an FPGA could be a DSP, but could be something different. Just only a logic switcher or a full-size DSP. And everything I created in the VHDL code could be used to create a DSP. But yeah, of course, I did this for learning purpose. And I could use a Shark DSP or other DSPs, but then I had a full-featured over GUI where I could select equalizer, compressor, noise gate, and so on, and drag and drop it to how it's called, a program, and connect all the lines, and then I have everything ready. But this was not my intention. I wanted to learn how digital audio could be processed, and for this I had to go down to the very low floor and learn everything from scratch. But you're absolutely right. DSPs are fine, and they are really capable of doing audio and video processing nowadays.
And you said you started from scratch, from the ground up. So there's a related question: how beginner friendly is this Vidor 4000 board for someone who is new to FPGA development?
Yeah, it depends. It is very easy if you are using the Arduino libraries, because they did a really great job putting a very complex system to very few lines of code. So I think you need 5 lines of code to initialize the FPGA and to initialize the camera and the HDMI system. So that's everything within the original logic. If you like to get in touch with the VHDL and the FPGA itself, then a few more steps has to be done. But as I showed you, you can install Quartus, and the very easiest logic would be an AND or an OR gate, for example. And you can, maybe let's zoom in for some inputs.
It's a great starting point. It's basic gates.
Yeah, I think so. You have an input here. You could have an output. This is this one, and you could double click here. Oh, let me find a free space here. Double click here, go to the primitives, go to logic, and then you could have a 4-input AND or a 2-input AND, and you can put it here, put it the inputs. It's another double click, and you can add here some pins. So input pin, and the same for output. And then you can compile it, upload it using the Arduino IDE with some tricks. It is not the intended way of doing this, but it's quite simple if you are reading the Elektor article. We described everything here. And yeah, then you can get in touch with VHDL and can use this. And then the same I did, you can go up in the complexity, and then you, at the end, could make an audio processor.
And question came up here in the comments. Is there a link for Christian's project? If I share my screen again, you just go there and search for Nöding. You're going to need to know how to do an O with an umlaut to find that. But alternately, there's the introduction to the article, which is a premium. You have to be logged in for this. But our magazine's coming out soon in the next few days. So the March edition, you'll see part 1 of Christian's as we highlighted earlier, and then he will have a follow-up. But this is a great starting point. I don't know if you can see the link up there, but good luck if you can't. Okay. Shall we go back to your screen, Christian?
Yeah, sure. Yeah, when everything worked here and the audio processing was done, I was curious what I could do with this technology basis. And yeah, I thought maybe I started this project with a defective Behringer project. Why not use a working project, working device? And here in my back, we see one of my mixing consoles, and I'm playing playing the trumpet in one of our big bands. And with big bands, you have a lot of number of channels in your system. And yeah, I created an expansion card for this audio mixing console based on this audio player or audio mixer to increase the number of channels I could mix in real time. So in general, this board behind me is capable of mixing 32 channels, and the Vidor FPGA was capable of doing this too. So 32 channels within the Vidor 4000 and 32 channels within the original console. And the Behringer console is able to combine input and outputs in a special way so that I could bypass inputs, analog inputs, to my self-made audio mixing expansion card and put it back to the Behringer system as a stereo channel. And then this increased the total channel to 64. Of course, in one of the comments in the YouTube video, they said, why are not using a up-to-date Wing console? But yeah, again, this was mostly understanding what the Behringer guys did here in the digital domain and what commands and communication protocols they were used. And yeah, you can see it a bit clearer what I did here. The Vidor 4000 board in the center. Next to this Vidor board, there's an Ethernet connector, the SD card, of course, for the Wi-Fi and the web server, and a DMX 512 connector, because this was one of the drawbacks of the Behringer console. I put this on the stage and I needed a different computer to control my lights. And I figured out how to implement the Mackie MCU protocol to insert via MIDI the, as you can see here in the small LCDs, the informations about the text. And I could read out the faders. and I could implement a full-featured DMX controller inside the SAMD21. This is one of the controllers of the Arduino Vidor 4000. And now I have a 64-channel audio console with DMX 512 features. So it's really great. I only have to take this with me to make my stage light and sound. And here
That's
you
awesome.
can see how I did this. So again, it's the same project as the audio player. I only put in here 4 times this so-called TDM. It's a time digital multiplexed signal. It's basically the same as I2S, but not only with 2 channels, but 8 channels. And it was pretty straightforward. I put all 4 lines to the Vidor 4000 and put 4 lines back to the X32. And then I had 32 channels to the mixing console and 32 back to the console. And everything is controlled via the SAMD and the ESP32. And in the logic, I have my audio mixing capabilities, my equalizing, 1 compressor, and a noise gate. And yeah, the control and the communication between the X32 and my Vidor is done using UART. So a pretty easy communication protocol. And yeah, it was fun doing this. And yeah, lessons learned: don't throw away your defective devices and try to repair it or make use of it. And even complex digital systems, yeah, could be used in a DIY project, because most of the industrial companies using basic protocols, and even computers with 64 bits and AI are based on the most basic protocols sometimes. SMB bus, for example, in the modern computers are a plain I2C, and we are using this in the maker domain too. Yeah, and
Chris,
again, just start a project.
Chris, the VHDL code for all that functions, is that also how we all program microcontrollers? We find example code in the internet, and then we copy and paste and try it out, and then later we adapt it to our needs. So in VHDL.
Yeah, sometimes this is easier than copying C code, because in VHDL you have a pretty well-defined input and a pretty well-defined output, and you can simply copy and paste it without thinking about dependencies. In C, if I copy something and someone used library, for example, then we have a pretty long tree of dependencies. And this is not the case in VHDL. So it is much more easier. It's easier to copy and paste this and use it, simply use it. Yeah.
And Christian, I want to ask you a technical question that isn't electronics based. Now that I have you in solo view, great studio you have there. I notice your desktop is curved. Did you make that yourself? Custom design?
Yeah, this is custom design because I needed some more space than in a regular desk. And yeah, this is wood, and I cut it with a saw here and made a circle and cut it by hand. Yes.
Nice. And you've got very clever use of the lighting. Nothing shining directly in the camera, but it's a very attractive studio there.
Yeah, thank you.
And you can,
yeah,
of
I
course,
lost my
I was going to say, you can, of course, use an Arduino Vidor 4000 for LED blinking, but you say it's possible to do more than that.
Yeah, you can do everything with this. Sometimes the logic is a bit limiting, but yeah, you could use a bit more expensive FPGA with more logic elements, and then you can go up in the stage. And the Cyclone is one of the most easiest FPGAs Intel is offering. And of course, Xilinx or AMD have pretty Lattice, for example, to not only want to know to tell you about one company, they are offering great FPGAs to start. And if you understand the most simple FPGA, you can go up with the the better FPGAs here.
Yeah, I understand basic digital logic from AND and OR up to parallel, look-ahead carry adders. So I think with that foundation, it wouldn't be too hard for me to get started on FPGA, right?
Yeah, I think so, yeah. Sometimes when I was in my study 2003, they said, "Oh, VHDL very hard to learn," and so on. No, just started. Sometimes you need a bit of paper, a sheet of paper, and draw some clocks and put the necessary signals you try to understand, and then start from scratch. Take your time, take a cup of coffee or tea, and then it will flow. It's much easier than C and other programming languages, because everything is clear what happens. You have a clock that is rising, and then all signals have to be in place. And if you take this simple rule, everything is possible.
That's great encouragement, because I'm good at C, and you say it's easier than C. Lovely.
I think so, yeah.
I put this comment up earlier, but I just want to highlight it. Dave says, "Great to see us interviewing authors of projects in Elektor. Please keep them coming." Well, if today's anything to go by, yes, it's a great idea. Very interesting topic. Here's another comment. "Great job, Doctor. Hi from Chile." Well, welcome, Chile.
Hi,
we had North Carolina earlier. And what is next on your schedule of projects that you'd like to achieve?
Yeah, I have some projects. Well, let me grab one. A couple of days ago, I had a good shot at eBay, and maybe I can put it here. It's one of the very old cards from Altera. It's not in the focus, but it's a PCI card, and there are 3 FPGAs, or they called it PLD back in 1998. And this card is capable of connecting a 5-volt logic directly to the PCI connector. And I'd like to understand how PCI is working and plug and play. Because now in the days, everyone is using USB and Ethernet, but I never built up a DIY card for my old retro computers, and I'd like to understand how PCI is working. And then, of course, as I have a good technology basis here for audio devices, I'd like to create my own sound card. So for retro gaming, I have, of course, a Sound Blaster 16 here, but playing with a DIY sound card is even much more fun. So yeah, this is on my projects at the moment. I'm pretty in a good way to manage how PCI is working. The PCI specs are quite good, quite well documented, and some of the logic is already there. And I managed to connect my modern computer to this card over JTAG, and yeah, I'm looking forward if this is working in the couple of weeks.
Well, that sounds like fun. And I do like what you've done with the DMX 512 connector to reduce the number of boxes. That's exactly why I was interested in using Raspberry Pi as a synthesizer, trying to reduce the number of big power-hungry boxes. And like you say, you need an extra computer to run your lighting, but not anymore.
Yeah, right.
And how complex is the DMX 512 protocol? First question. Second one, is it a differential signal?
Yes, it's the current-based signal. It uses RS-485, and I need a special transceiver for it. But in the processor, it's simple UART connection. So first, I tried to use the ESP32 to output DMX 512 because there are several libraries for my ESP32, but none of these were working together with the other 2 UARTs I'm using to communicate with the FPGA. So I had to rewrite everything from scratch for the FPGA. So the DMX 512 is generated within the FPGA, and maybe we can have a look here in the project. I'm not sure if we have time enough for this, but only a short look.
We've got a few minutes left.
Managed to find it. Yeah, okay.
It's
Depends on
quite
how fast
simple
the computer is.
protocol.
Yes,
I would say.
it's straightforward. Okay, it's not loading at the moment, so.
Never as straightforward
so
when you're demonstrating live.
Ah.
So Jens, you do some music streaming in your hobby time. Do you also use DMX lighting?
In my studio during the streams I'm using it, but I have a ready-made controller for my desk. But I think once I did some experiments with DMX because there was an Elektor project, and I think it was an Arduino add-on board, an Arduino shield, and yeah, I think it's quite easy to program something, to control something. Of course, it's a little bit more complex to have then a working tool where you really can control many lights. But Chris, I think you also did such things, and it's actually still available. UPC demo program.
Yes, right. It's an open source tool to control lights like moving heads, scanners, and RGB LED bars. Yes. Mm-hmm. And now it opened, so it's about 37 lines of code. Oh no, it's counting wrong. I found a bug in the program. No, it's the Zoom. 237 lines of code. Not code, logic lines, and it's a simple state machine. And I think it's too much if we go in the last 4 minutes through this code here, but I'm only looking at several stages for the breaking part, the mark part, and then I have a counter and I will wait a number of clocks here in this state, and then I go to the idle state, then I go to the sending part, send out the individual bits, and then I go back to the idle part. And yeah, it's pretty straightforward. And again, as I said, I used a piece of sheet of paper and draw the individual states and the transitions, and then I coded the state machine without the internal logic, and then I put the logic there. And yeah, it took me around, I think, 2 evenings to program this, but there are pretty good documents in the internet showing the individual signal lines of DMX and in which order everything has to be sent. Yeah, and that's it. Everything is open source, and you can have a look in GitHub. Feel free to use it in your own projects.
That's great. And it's a lot of good information. And what I like about these live streams is that they do get recorded. We often get asked that. If you want to rewatch this, just come back wherever you're watching. YouTube's my favorite, but I mean, you can even watch this on StreamYard, where a lot of people are. Watch it again. A lot of interesting stuff. And if you pause enough, you can get a lot of good information, because we've just shown the highlights. So we are reaching the top of the hour. Jens, do you have any further questions for our esteemed guest?
No, not at the moment. I'm looking forward to have maybe other contributions from Chris, because he's doing so much at the moment. So yeah, maybe there will be other Elektor articles.
Yeah, it's great stuff, very interesting. And we've only highlighted part 1. I'm looking forward to part 2 of this as well. Thanks so much for joining us, Dr. Christian Nöding, or Chris, as we call you, taking the hour.
Thank you very much.
Great of you to put this all together for us, and great article. And Jens, hope you have a good time there at Carnival in Cologne. And from my side, and to our audience, thanks for joining us from around the world. Good luck to those of you entering the competition. I'd also like to start learning about FPGA. I have been wanting for 30 years, but some things you just never get around to. Wish me luck. Thanks a lot, and good night, and good afternoon, good morning, wherever you are in the world.
Thank you. Bye.